Hello, in this video I want to talk about definite integration. And really it's just before we get into some really cool stuff like the Leibniz rule or what's otherwise known as Feynman integration, things like the bracket methods or different methods of reduction and ultimately higher integration techniques and applications within physics. I thought I would start with, or I thought I'd dedicate a bit of time, just a couple of videos on some of the basics or some of the core skills. And so in this video, we're going to focus on definite integration. But what we've got here is some of the basic properties of indefinite integration. Indefinite integration. And I'm not going to spend much time at all on this. There are already many fantastic videos out there that offer the very earliest of introductions to integral calculus and will cover these basic properties, but in any case it might serve to just do a very quick review or revision. And what we've got here is that for example, is that if we want to integrate some simple function with respect to x, so in this case x raised to some power, the standard results, if you will, is that we're going to have x raised to n plus 1, and all that's going to be over n plus 1. So, in differentiation, we know we take 1 off the power. Well, with integration, we add 1 on to the power. And then we also set all of this over that value, so the n plus 1. And of course, we always generally want to think about adding on the constant of integration. So for this second property, this is just the same as the first, but we're adding a constant, right, in front of our x raised to n power. All that this is stating is that you can pull out your constant, any constant as a kind of coefficient in front of this xn term, and you can pull it out in front of the integral, just as we see here, and then you can integrate as normal, just as we've done up here, where we now just have x raised to some power, so x to the power of n. And then once you've done your integration, you can just multiply by that constant. And that's all that this is stating, this second line here. And finally, we've got the other property or rule that if you're integrating some constant, and this is denoted by a, so some constant with respect to x, what you'll end up with then is that constant times x plus c, right? So ax plus c. So that's just the that's indefinite integration. Those are some of the first rules that one will learn when they first pick up or first introduced to integral calculus. But what is definite integration? This is what we want to spend time thinking about in this video. And so definite integration, there's a very general way to write it, and then I will sort of, I suppose, explicate and just describe some of the nuances. But what we want to do is we have our integral sign as normal, and we have our limits of integration, otherwise known as the limits of the integral. And so let's just keep it general, so we'll say from a to b, right? And we're just thinking generally here. And we have our function, which we'll denote as f prime of x, right, to use prime notation. Then we're integrating, in this case, with respect to x. And this equals, when we integrate, use definite integration, we at the first, what we'll maybe call the first phase, I suppose, where we use square brackets. I mean, then we have our f of x, right, because we've integrated this. Now it's f of x. And we want to state the limits of our evaluation. So we put it in square brackets, then we restate our limits of integration. And then this is the final phase called the evaluation. And we can denote this as f of b minus f of a. Cool. So what does all of this mean? Well, as I said at the outset, you notice that we have two values here. We've stated them generally, a and b attached to the integral sign suddenly. These are the limits, what is stated as the limits of the integral, okay? And in this video, we're treating these as constants. However, when we get into the really cool stuff like Feynman integration and etc., you know, we're going to be working with evaluating some really cool integrals where these limits aren't going to necessarily be constants, and in fact they can be differentiable functions in themselves. And so that's where all the fun really starts, I think. But in this video, we're treating these as constants. So let's just think about them as constants. And we can think about them, offer some intuition about the limits of the integral in the sense of, like, let's just draw some arbitrary curve, like something, I don't know, something like this, let's just say, right? And we'll just mark this point. Let's just say that this is A, this is the point A, and this is the point B, okay? So this is, another way to state it is that A, this is where x equals A, this is where x equals B, right? So here, x equals A, x equals B. And what we're doing is essentially, in this case, we are finding the area under the curve between A and B. That's what this all means, basically. And so you can think of integration or the integral as the sum, okay? So it's the sum of many trapezia, very small, and they get smaller and smaller and smaller, and I can't quite draw that, but there's a wonderful proof that we could cover in the future that kind of illustrates all of this. And basically you're taking the sum of all of these trapezia that's going to give you a very close approximation to the area under this curve. And in future videos we'll expand on that idea, for example, in things like when it comes to volume by revolution. So we'll say, okay, we have this curve, we have limits of integration, but what happens if this is rotated then about the x-axis, something like this, right? It's rotated about the x-axis. Well, no longer are we dealing with area, right? A 2D slice, if you will, but we are dealing with volume, and there's a really cool formula for that, but that's for the future. But this is just to give a sense of what the limits are, right? The limits, we're trying to find the area under a curve, and in fact, we can kind of limit our focus to that in this video. And also, you know, we can think of something like this, like if we have another arbitrary curve, and it could even be similar to the one we had before, something like this, and let's just say that there's a line that kind of runs like this, okay? And so it kind of keeps going on, and we need to find the area under the curve in between the line, right here. Okay, there are many different techniques to figure that out, and so we can cover all of that, but on our way to the real cool stuff when we get into multivariable calculus and you know, some of my favorite methods for solving incredibly difficult functions, or evaluating incredibly difficult integrals, such as Feynman integration and stuff. So this is the basics right here. This is definite integration, and we have some sense of intuition. And let's just go over kind of the stages, I suppose. You call it phases, call it stages, okay, of definite integration. So here we state, this is the statement. We could call this the statement. So let's just write that. This is the statement, this part right here. This is the statement. So we're stating that we're integrating between some limits of our function with respect to x. That's our statement. This part here, this is after integration. Call it after integration. And formal notation will have it that we set this in square brackets, and we essentially restate our values of evaluation, our limits of evaluation. And thus this stage, this final stage, is called the evaluation. Okay, and we use round brackets, formal notation, to use round brackets here. But let's just work through an example. Like, we won't think about it in relation to its graph or anything. Let's just draw up a general example, and we'll go through it all. So let's just say, like, I don't know, we're given something like say we're asked to evaluate something, let's just say from 1 to 4 of some function f of x. So let's say we are given 2x minus 3x to the 1/2 power. And let's add a constant. Let's say just plus 1, and we're integrating with respect to x. Alright, so what do? Well, we've sort of covered the general idea of definite integration and its 3 basic stages. So let's just work through it one stage at a time. And so here we can we could pull. No, let's just keep it like this. And so we'll say, okay, we're going to now work toward our after integration stage. So we want to integrate basically all of this right here, all everything in the brackets, or f of x, if you will. And so to do that, what are we going to end up with? Well, we're going to add 1 to the power here, right? So it's going to be x squared. We've got a 2 in front, and the 2's will cancel. But actually, I'll just write it out all explicitly. So we'll have 2x squared, and then of course we're setting it over our n plus 1, just as we went over here. So n plus 1, that's just 2, right? We found that out. And of course, like I said, these will cancel, but let's just write it all out. And we've got, well, we're adding 1 to this power, so that's going to be 3 over 2. So we'll have minus 3, and we've got 3 over 2, and then this, of course, is being put over our n plus 1, which is 3 over 2. And then we've got some constant, and this is just going to be x, right? And we want to put this now in square brackets. This is our after integration stage, and so we are integrating our limits. The limits of the integral are from x equals 1 to x equals 4. So let's rewrite that. And of course, the higher limit, if you will, goes on top, generally speaking. Okay, so put that up there. And we can tidy this up, can't we? Like I said, the numerator and the denominator are going to cancel here, so let's just do it. Let's just tidy this up. And again, we put it all in square brackets. It's just going to be x squared, right? They cancel. This is just going to be, well, you put the 2 up top, that's 6. Then you've got 6 over 3. That's just 2, so you're going to end up with 2x to the 3 over 2 power. Whoops, my pen tool lagged out there. 3 over 2 power, and we've got our x still. So we just put that, we close our square brackets, we restate the limits of our evaluation. And now it's the final phase, the final stage, if you will, the evaluation stage. And so for here, what we want to do is we use round brackets as formal notation, and we want to evaluate where x equals 4 and x equals 1. So f of b minus f of a. Well, f of b is the higher limit, if you want to phrase it that way. So we start with where x equals 4. So we say, well, we've got 4 squared, right? Because we have x squared. So when x equals 4, we've got 4 squared minus 2 times 4 to the 3 over 2 power plus 4. And now we're subtracting. We need to find the difference, and we've got our f of a. So that's just when x equals 1. Let's just plug that in. So we got 1 squared minus 2 times 1 to 3 over 2 power plus 1, and we close our round brackets. This is the evaluation stage. And so what we've got here is, well, we've got 16, right? We've got 16. We'll just work through it all. Here it's a very simple way, very quick way to think of this without going through more steps, just where I'll just write it right here, where just note that 4 to the 3 over 2 power is equal to 2 to the 2 cubed, 2 to the power of 3, and of course that's just equal to 8, right? 2 times 2 is 4, times 2 is 8. So then you have basically 8 times 2, that's 16. So we have 16 minus 16, and then we just got our 4. So plus 4, and we close that off. This is just, again, basic exponent properties. If this isn't not clear, just look that up. So here we've got, well, we've got 1 squared. So that's just 1 minus, well, this is just going to be, what, 2? We're adding 1, and you can see that we've got 1 plus 1, and we're subtracting 2. So this just reduces down to nothing. That's just 0. We've got 16 minus 16, that cancels. So really what we have here is 4 minus naught, which equals 4. Okay, so that is definite integration. Notice again, we're just to review, we've got our statement. It's a first stage. We've got our after integration stage. We use square brackets, restate our limits, and then we've got our evaluation stage.